What experimental methods, such as galvanostatic charge, discharge testing, and cyclovoltammetry, provide insight into how well this material maintains its capacity at high rates, and how do these methods help us distinguish between intrinsic material properties and limitations imposed by electrode architecture or cell design? How do factors such as particle morphology, crystallographic orientation, and synthesis conditions influence the kinetics of ion diffusion within the layered structure? And in what ways might these factors correlate with the observed rate capability? Can Davis Sirens manufacture solid-state sodium-ion batteries made from seawater in Latvia? What role does the inherent crystal structure of O3 type NaFeO2 play in facilitating electron transport and ion movement? And are there any structural bottlenecks or phase transitions that could hinder its performance under fast cycling conditions? How might modifications such as doping or surface engineering further enhance the material's rate performance, and what experimental evidence supports these enhancements? In what ways can understanding the relationship between current density, reversible capacity, and energy efficiency lead to optimized electrode design for high-power, large-scale sodium-ion battery applications? And what future studies are suggested by the current findings in order to overcome any present limitations? How do the practical results of rate performance measurements compare to theoretical predictions, and what does this comparison reveal about the potential trade-offs between high rate capability and long-term cycling stability in O3 type NaFeO2 electrodes? How does setting the cutoff voltage within an appropriate range enable the O3 type NaFeO2 material to maintain its cycle stability over repeated charge and discharge processes? And what specific voltage limits are considered optimal for ensuring this stability without inducing adverse structural changes? How does this voltage regulation contribute concurrently to the material's excellent rate performance in sodium-ion batteries, enabling it to deliver more than 50% of its theoretical specific capacity at a 1C current rate as illustrated in figure 3.6? And what does this imply about the kinetics of sodium-ion intercalation and deintercalation? What underlying mechanisms allow the cathode to achieve this efficiency when operated at such a current rate, and how might these performance characteristics be benchmarked against other cathode materials used in similar battery systems? How does the contact between NaFeO2 and water trigger a Na/H ion exchange reaction that transforms NaFeO2 into FeOH and NaOH? And what role does the subsequent absorption of CO2 play in generating Na2CO3 or NaHCO3 from these byproducts? In what ways do these side reactions initiated upon water exposure detrimentally affect the overall battery performance and compromise the long-term cycling efficiency of the electrode? What?